level still.
Yeah. Okay, it's not yet at saturation.
Yeah, but I think like in terms of the participants, a little bit of saturation is setting in because we are kind of averaging 80 people slowly. I think also a lot of end semester exams are going on in many places and so on.
Of course.
And all online. So.
But you're recording the talks, right? So we can watch.
Yeah, exactly. It's also live streamed on YouTube right now.
Oh, that's cool.
So
hello,
you know, so many people are also logging in there.
That's awesome. That's wonderful.
So maybe I should start now, like, and then as people are logging in. So I'll just give a quick introduction to Professor Martin Zwierlein, who is a professor at MIT. And he did his studies, undergraduate, masters, I think, in Germany and France, and then moved to MIT with Professor Wolfgang Ketterle to do his PhD. And I would say that Martin really entered the field of AMO with a bang. You know, we were at that time PhD students, and I remember that tremendous excitement. In fact, that's exactly the picture he has on his first slide. This, you know, this first demonstration of superfluidity of fermions, electrons. Like we were at that time at, I was at Cornell. I remember, like, you know, Dave Lee, Richardson, Sourav, in fact, Tony Leggett was like all these people there, like the entire condensed matter community was also shocked seeing those images coming out of Martin's PhD thesis. Eventually that became his thesis work. And I remember also like Kleppner making this comment that it's no, you know, it's not a smoking gun for superfluidity of fermions, but it's really a cannon, I think. And since then, I think with a short stint in Immanuel Bloch, Ted Hansch group, he moved back to MIT, actually inheriting a big and amazing legacy of science, starting from Dave Pritchard, BEC1, I think the experimental lab, which was inherited by Ketterle, Wolfgang, and then eventually by Martin. So it's an amazing academic, that's a different story altogether. But of course, he developed many other, you know, like 3 more labs, I guess, starting looking at like fermions in lower dimensions, this microscopes, and quantum microscopes, as well as I think molecules. That's what we'll be learning. So he has been firing the cannon since then in every way. And of course, like, you know, such good work is always recognized by many awards. I don't want to take a significant part of Martin's talk time to state any of that, but just to state one, you know, the most prestigious AMO award, II Rabi Prize, I think in 2017, he was recognized with that. Also, Martin turns out to be an extremely exciting and like enthusiastic and an amazing teacher with clarity. And that's what we'll be listening to. He will be giving 2 lectures. Today is the first one. And then Monday, same time, he will have the second one. So over to Martin.
Thanks so much, Saikat. And thanks so much for having me in this wonderful setting. I'm amazed that this works over Zoom. We can all connect and together talk and think about physics. And so yeah, I will actually talk in this first lecture about these fermions in the bulk and ask and hopefully answer how they can become superfluid. Because it's a nice story of what particles do when they come together and interact and decide that there are better things to do than run around lonely. And during this talk, if you have a question, you can really just, I guess the organizers will check the chat and please ask questions.
There will be chat and we'll just communicate.
Exactly. So you will tell me.
Before you start, I just wanted to mention one point that, you know, there might be some emergency here locally. So Professor Bimalendu is also there, and we might switch the responsibility of chairing and sharing the questions. So, okay, over to you.
Yeah. Yes, so if you want to read more about the whole endeavor of trying to control and understand Fermi gases, there are various reviews that you can read up on in the Varena notes, for example, but also there are wonderful reviews of modern physics by Giorgini, Pidevsky, and Stringari on the theory of Fermi gases, and by Emmanuel Bloch, Jean Dalibard, and Wilhelm Zwerger, generally on many-body physics with ultracold gases. It's a great starting point. And on superfluidity in Fermi gases, there's also a collection of lecture notes edited by Wilhelm Zwerger that's very useful to check out if you're interested in further reading. So to orient ourselves on the temperature scale where we are, maybe this is not needed after you have listened to several of these talks on cold atoms. But clearly, you know, we are not talking about temperatures inside a supernova. That would be 10 to the 9 Kelvin. The center of the sun is still very hot. Your living room is okay. Outer space again becomes uncomfortable. Look where cold atoms are. They're far, far on the left side here of this log temperature axis in the nanokelvin regime. And to give a sense of scale for the typical velocities we encounter in a supernova, you would be so fast that you get to connect New York to Paris in 10 seconds. Great, but of course you wouldn't arrive in one piece. In your room, particles run around with hundreds of meters per second. No surprise, the speed of sound is 300 meters per second. These are connected actually. And at low temperatures, atoms in our lab, they move at the speed of a snail, millimeter per second. What happens at these low temperatures, if it was all about like things getting slower and that would be it would be a bit of a boring story, I admit. But no, luckily, de Broglie taught us that at very low temperatures and low velocities, therefore, we will have a wavelength describing particle motion that becomes very large and observable. So the de Broglie wavelength is just given by Planck's constant divided by the particle mass and the velocity. And so we can ask, you know, what the size of this de Broglie wavelength would be at the various temperatures. Before I go there, we can also think of this in Heisenberg's way, this length scale giving us the uncertainty with which we know where each particle is. At very low temperatures, I have a very good knowledge about the momentum of the particles, delta P. So I stop knowing precisely where each particle is. It becomes smeared out over some uncertainty blob on the order of h divided by this uncertainty in momentum. And so at very low temperatures, these wave packets, which tell me where the particles are, they just broaden. And at some point, we, of course, have the interesting question, when we look at the gas of particles, it should no longer be described by gas of point particles, but at low temperatures, we should start thinking about waves running around. Now, as long as the uncertainty of where each particle is still much smaller than the distance between the particles, we are not in trouble. But of course, as the temperature lowers, this uncertainty grows and grows, and at some point we get into trouble with quantum statistics. We have now an uncertainty on the order of the interparticle spacing, and now it depends, do we have bosons, do we have fermions? And in a very nice little cartoon that a friend of mine drew, we can see what the two different ways out are. For fermions, they are kind of antisocial particles. They don't want to be, they cannot possibly be in one and the same state. So they form a Fermi sea, as it's called, where each particle sits on its own quantum state, if you want. And look how antisocial they are. This guy's spying on the others. This guy is listening to his or her own music. This guy is even Pauli blocking himself up there. So antisocial. As you cool down a gas of fermions, they will just gradually form a better and better defined Fermi sea with less and less holes in this ladder of occupied states. There is no phase transition. However, if you do this with bosons, you see they are the happy particles. They start to form Bose-Einstein condensate at low temperatures, and see they even help each other into the ground state. This is called bosonic stimulation. So there is a phase transition at low temperatures, even without interactions, and that is the Bose-Einstein condensate. Now we can draw an artist conception of the fate of bosons at low temperatures. They will just form this one beautiful, big, fat matter wave, n bosons all sharing one and the same macroscopic matter wave. For fermions instead, the picture should be this one, where you see each of these little fermions, they have their own wave packet and they need to stay apart from each other with an exact, making sure that they're not overlapping at all. When I made this cartoon, it was around 2009 or so, I felt, okay, that's a nice cartoon. But these days in optical lattices, we can take pictures where we see precisely this situation in front of our eyes, basically, in front of the CCD camera, where each fermion indeed occupies a different lattice site in an optical lattice, directly showing the Pauli principle at work in real space. I will talk about experiments in optical lattices on Monday, so I will show some of these pictures. The condition to get there, to get to this quantum degenerates regime, is apparently that we have to get this uncertainty down, and this position uncertainty so large that it becomes on the order of the interparticle spacing. That's the condition that Einstein wrote down, which gives us a degeneracy temperature scale that depends on the density. So at high density, it's easier to reach, but of course at high density, maybe the system that you have instead rather likes to form a solid. So we have to work with ultra dilute gases so that the atoms don't realize that they would much rather form a solid, and that forces us to work at very low temperatures, below a microkelvin. Let me say also that even at 0 temperature in a Fermi gas, this energy scale is still important because the fermions still keep their distance, even at 0 temperature, on the order of an interparticle spacing. So this energy scale still gives you the typical energy of a Fermi system, even at 0 temperature. It's called the Fermi energy. If you look at the temperature scale, what are the typical systems? And if you ever wanted to touch a degenerate Fermi system, just touch the nearest metal that you can find, and you hold the degenerate gas of electrons in your hands. At room temperature, these electrons are much colder than the Fermi temperature, corresponding to the Fermi energy, which would be many 10,000 degrees of Kelvin. So it's a beautiful degenerate gas of electrons. White dwarfs are stars that are held together against gravitational collapse just because of the degeneracy pressure between the electrons in this star. And neutron stars are even more compact objects held together against further gravitational collapse due to degeneracy pressure of the neutrons making up the star. So it's an amazing object, 11 miles in diameter, and it packs in more than the mass of the sun. On a sort of more human scale, liquid helium at a few Kelvin becomes degenerate. And as you know, there are two species of helium. There's helium-4 and helium-3. Helium-4 is a boson. Helium-3 is a fermion. Helium-4 already becomes a superfluid below a few Kelvin, at a few Kelvin, because that's when it actually undergoes Bose-Einstein condensation. Helium-3, however, it can also become superfluid, but that occurs at a much lower temperature, around a few millikelvin, because these fermions first have to pair up before they can become superfluid. And we will learn more about fermion pairing in this talk. Our ultracold Fermi gases, they live below a microkelvin. That's where they become degenerate and where we can hope for seeing interesting effects. So now in these days, we have these fermions in a happy box potential. It's really like a Coke can full of fermions. Now the Coke can is not formed with aluminum walls, but with walls of light in our lab. So we shape green light, which acts as a repulsive wall to our fermions. Green light in the form of a Coke can, so to speak. So a round beam that is a ring of light propagating one way and two sheets acting on as end caps of this box, providing a wonderful potential where the atoms inside this box don't see any light. Only when they hit the walls, they bounce back. And so then you can actually study homogeneous Fermi gases, which is quite nice because it's much easier to understand things like transport coefficients or complicated questions where you would really rather want the density to be uniform. So it's a theorist's dream to start with an experiment where your density is uniform. And the first thing that you want to check when you have a box of fermions is whether Fermi and Dirac were right in writing down their distribution for fermions. So Fermi had this brilliant idea that Pauli's principle should also be applied not only to the internal states of electrons inside, for example, the hydrogen atom, but also for the external states of motion of the particles. So that gave him the expression for what we now call the Fermi-Dirac distribution that tells us fermions can only occupy each momentum state exactly once, not more than once. And so if you look at the time of flight distribution of the momenta of these fermions in the box, you should find precisely this Fermi-Dirac distribution where 1 here means I have exactly 1 fermion per momentum state. And as you cool down the gas, you start seeing the formation of a Fermi surface at low temperatures. So the 1 here is precisely Pauli blocking. It's not possible to stuff in more fermions than 1 per momentum state. And you start forming the Fermi surface. At 0 temperature, it would just look like a wonderful theta function. Everything occupied up to 1 and nothing occupied beyond 1 in units of the Fermi velocity. Clearly, we're not at 0 temperature with this experiment, but we start seeing the formation of this Fermi surface. So these folks are very happy. This was at the 90th anniversary of Fermi and Dirac writing down this distribution. By the way, it's hilarious. Dirac wrote it down half a year later than Fermi. And Fermi wrote him a little nice postcard saying like, hey, so beautiful paper, but I wonder whether you knew of my earlier work on the distribution. And Dirac said, oh, wow, yeah, now I remember. I actually did read it, but at the time I completely, just forgot about it, disregarded it because it was not directly in the direction of my research. So, I mean, it's how it happened, but it's the 2 papers are kind of orthogonal in how they derive this, and both are amazing pieces of science. Good, so that was the story of non-interacting fermions. We know interacting fermions make everything around us. They're really the building blocks of matter. So on the left side, I have a nice example of a lithium-6 atom, which is my favorite atom, actually. It has 3 protons, 3 neutrons, 3 electrons. All of these are fermions. And an uneven number of them makes another fermion. So the entire lithium-6 atom taken as a whole is a fermion. In neutron stars, of course, neutrons are fermions, but in the center, maybe there is a soup of quarks. So people talk about a superfluid of quarks that might be in very dense neutron stars at the center, where the quarks are forming a superfluid. So we need to switch on interactions between the fermions. And I want to explain to you how this can work in an ultra-cold gas of atoms. So for that, we have to first understand what the interactions are between 2 atoms. At long range, there is van der Waals potential coming from the fluctuating dipoles that one atom can induce into the other atom. It's a fluctuating dipole force. It's the second order dipole-dipole interaction. That's why it goes like 1/r⁶ and not 1/r³. And it's always attractive because these 2 atoms are in their ground state. So once you switch on this second order process, it will lower their energy. Good. So it goes like some coefficient over r to the 6. And at very short range, well, now the electron clouds of the two atoms can start to overlap and really they want to avoid that through their strong Coulomb repulsion. So at short range, the interaction potential will climb up to infinity. So this gives you this characteristic interaction potential of a certain scale, which is given by the van der Waals range, which has to do only with this coefficient C6, the mass, and h bar. Now we have to remember that we work at very low temperatures, where the de Broglie wavelength is already macroscopic on the order of a micrometer. So it turns out a micrometer is much larger than this van der Waals range. So the van der Waals range is just on the order of 50 to 200 Bohr radii, depending on what atom you work with. So that tells you we don't have to know anything about this interatomic potential. You can forget what I said, and we can say, we can just remove all the intricacies of this potential. The atoms do not even resolve it. They are blind to it because they have a much larger wavelength. Then they need to resolve the details of this potential. And we can replace it basically by any other potential we like at short range. But one thing has to remain the same, and that is the so-called phase shift that two atoms acquire when they scatter off each other. Let me explain what that is. Far away from the potential, the two atoms will be in a free state. They will have a wave function that goes like the sine kr. They're free. But that sign can be phase shifted, and it will be phase shifted because of this fact that they are interacting at short range. So that's all that can happen at low temperatures, that the atoms acquire a little phase shift delta. So if you give me some other short range potential that can give me the very same phase shift, I can throw out the van der Waals potential and use your new potential as a pseudo potential, and I will be able to describe the physics equally well. So for example, let's take a happy square belt potential, because we learn it in the textbooks, and ask what happens as I change my square belt potential. There is a new length that we have to learn about. It's called the scattering length. It has an expression in terms of this phase shift that basically says the scattering length is, roughly speaking, the zero crossing of this wave function. I will explain it better in the next slide, what it is. It's, roughly speaking, the place where you have the first zero crossing here. This is a better slide for the scattering length. You know, at very low temperatures, you're not even seeing that the wave function goes like the sine kr. It basically goes like kr, basically goes like a linear function. And that linear function looks like as if it emerges from some origin, which can be at negative distances. You know, it's not a real origin. It just looks like as if this line was coming from negative distances. Then you have a negative scattering length. And that can come about because you have a slightly attractive interatomic potential. So now let's increase the depth of this potential. And when you do this, you're pulling the wave function and you're going through a resonance, getting one more bound state into the potential. And the scattering length switches from minus infinity to plus infinity and back to positive values. See, now I have a situation where the wave function appears as if it emerges from a positive zero crossing. So the scattering length is positive. I pull it a little bit more. I go through another situation where now the wave function looks like it originates from negative distances. And I can pull more, and I retrieve again a situation where the scattering length is positive. So all that's this interatomic potential has to do is it has to give you the correct scattering length of the real potential, and then you're fine. So here are the three situations that can happen with this tunable square well. For weak attraction, you don't have enough attraction to give you a bound state. Your scattering length is negative. It looks like as if your wave function originated from negative distances. A resonance appears right when you have enough energy for one bound state to appear in the square wave potential. Your wave function bends so much that the wave function continues with a slope that's horizontal. So it looks like your scattering length is either minus or plus infinity. You cannot distinguish. You pull it a little bit more, and you get to this situation where the scattering length is positive now. And that means you now have a bound state in your interatomic potential. And you can prove that to yourself by realizing that outside of this square wave potential, you can also solve the Schrödinger equation with a bound state solution, an exponential decaying solution, instead of something that goes like sine kr. So for positive scattering length, you have a bound state. For negative scattering length, you don't. Good. So now, can we tune our van der Waals potential in the lab? No, we cannot. But there is a trick. What will be important, of course, in the following, eventually, for many-body physics is that scattering length that I'm tuning large or small compared to the interatomic distance. So you will see this parameter 1 over kFa appear all over the place. And this simply measures the interparticle distance, which is 1 over this Fermi momentum kF. It's roughly simply the Fermi wavelength, measuring the interparticle spacing, divided by the scattering length. So if your scattering length is small compared to the interparticle distance, that's a weak interaction for the many-body system. If the scattering length is comparable or much larger than the interparticle spacing, now you have made a strongly interacting system. Good. So with this theory baggage, we can ask, how can we actually tune this potential? Here is what would happen if you only had a single potential to play with. The atoms would come in to this interatomic potential and come out, and they would have one particular scattering length, and it would be whatever nature gave you. But for alkali atoms, there are always two potentials that are relevant: the so-called triplet and singlet potential. Those are the potentials for two atoms that have their electron spins aligned, that would be the triplet potential, or anti-aligned, that would be the singlet potential. And the beauty is you can tune these potentials with respect to each other and bring a bound state of, for example, the singlet potential into resonance with the energy of two atoms in the other potential. And that gives you then a resonance. How to do that? It's very simple. You just change your magnetic field in the lab. Why? Because the Zeeman effect will, of course, tune the triplet energy up and down thanks to the Zeeman effect, whereas the singlet potential will not budge. It will not move. So you can tune your triplet potential into resonance with the energy of a bound state of the singlet potential. Then you have a resonance. So two atoms come close together and then realize, wow, there is this molecular bound state nearby that we could populate. So they will spend a whole long while virtually trying out this bound state before eventually they leave again, finding out they don't have quite the same energy. That will give you a Feshbach resonance. So this is the picture. If you plot the scattering length that we have just discussed for the square wave as a function of magnetic field, you will see this beautiful resonance. And on the left side, where the scattering length is positive, you have a bound state available in the interatomic potential. On the right side, where the scattering length is negative, you don't. So that's the recipe how to make strongly interacting gases. With these strong interactions, we are now in the position to connect to many interesting systems. Of course, they're all very complicated and much richer than our gases in the lab, but they all share similarities. For example, nuclei consist of neutrons and protons, you can think of those as being the spin up and spin down, actually iso spin up, spin down particles of a two-spin Fermi system with very strong interactions. Or neutrons in a neutron star also are very strongly interacting spin 1/2 objects. And in the crust of a neutron star, you have a situation very similar to these strongly interacting gases near a Feshbach resonance. And on a human scale, these high TC superconductors, they are really, really complicated. However, at the basis of them, people think they can be modeled as a spin 1/2 Fermi gas, hopping around in an optical lattice and interacting with each other. And even that simple model is not solvable. That's why cold atoms have strong hopes to actually provide insight into these complicated problems. It gets even worse if you start talking about dynamics. So you have nuclear fission going on, which would be amazing to study, to understand from first principles, but it's bloody difficult. Or neutron stars merging with each other. There must be a hell of a friction and complicated many-body effects going on. It's just very difficult to study. We can now listen to them thanks to LIGO. But it's very complicated physics that undergoes such a neutron star merger. And of course, in these superconductors, we know there are phases, even above the superconducting phase, where we have strange things happening, where the transport properties are unusual. That's why we give names like strange metal to these phases, because it's a metal that does not behave according to the usual rules that metals should obey. For example, the resistance doesn't grow with the square of the temperature, but only linear with temperature, and so on. So there are lots of unsolved questions about strongly interacting fermions already in equilibrium, but even worse once you kick them out of equilibrium and have a non-equilibrium situation. So it's very interesting to study idealized models like our gases in the lab. Good. I would like to think about, a most direct and brutal experiment to do to understand these interactions. And well, physicists love to smash things into each other. For example, here at the LHC, where you can recreate the Big Bang by colliding heavy nuclei into each other. This creates a quark-gluon plasma, a strongly correlated soup of fermions glued together by gluons. And it is believed that this quark-gluon plasma, which was there at the very first split second after the Big Bang, is sort of a perfect fluid. It has very low viscosity. And this is a nice view inside the LHC. You have seen this picture many times. There's a little person down here to show you the sense, give you a sense of scale. This now is the BEC1 experiment that Saikat was mentioning in the beginning, where also for scale, we have a little person here showing the size of the experiment. Of course, this is a joke. The experiment is very much on a human scale. We do use this person here, very useful, to reach the tiny mirror in the back here to adjust the green light going in. And in this experiment, we did what we call the Little Fermi Collider, LFC, clearly, where we smash a spin-down Fermi gas with a spin-up Fermi gas right at the Feshbach resonance and see what happens. It's a collision at 100 pico-electron volts, okay? So that's 23 orders of magnitude smaller than what the LHC can do. It does not cost 23 orders of magnitude less than the LHC, I will say. And let's see what happens in such an experiment. First, I will switch off interactions, which we can do also in these gases. Thanks to the Feshbach resonance, we can make sure there are no interactions at all. And these two atom clouds will just trade places. So they spin up and spin down. They just move through each other as if there was nothing. And indeed, there is nothing, no collision. What happens for resonant interactions? The two clouds smash into each other and jump back from each other. They are so strongly interacting that they're almost not interpenetrating. In fact, it takes a long time, on the order of a second, for these two gases to penetrate and diffuse into each other. And it has a very slow time scale for diffusion. These are the stills from this movie. The difference density showing you this collision, and the total density showing you this region of very large non-linearly enhanced density as they bounce into each other and then fly away subsequently. As I mentioned, it takes a long time for them to interpenetrate each other. We see here the first frames of the movie, but since the atom clouds are still in a trap, they bounce back into each other several times. And even after 200 milliseconds, they're not on top of each other. It takes a second for the two clouds to completely merge and lose any trace of their magnetization, if you want. Even after half a second, if you look at the spin composition, you see still mostly spin up on one side, spin down on the other side. What makes it take so long for the two clouds to merge? In fact, the mean free path for collisions is as short as you can possibly imagine. It's as short as 1 interparticle spacing. That's how strong you can make interatomic collisions at the quantum limit. They have to collide at every encounter. It's very different from a typical gas in the air right now, where particles have to move many, many interparticle spacings before they eventually collide with another atom or molecule. You can therefore back out the diffusion coefficient. A diffusion constant is always something like the mean free path in the gas times the average velocity of the particles in the gas. The mean free path is this very short interparticle spacing. The average velocity we know from de Broglie for this Fermi gas has to be something like h bar over m times the interparticle spacing. So then you cancel those two interparticle spacings on both sides, and you get a diffusion coefficient, which is universal. It's a quantum limit of diffusion. H bar over m governed just by Planck's constant divided by the particle mass. And in terms of real numbers, this is 100 microns squared per second. That's precisely right for our experiment. Our cloud size is on the order of 100 microns, and it takes on the order of a second for them to diffuse into each other. So we are right there seeing the quantum limit of diffusion. It's very nice to mention the analogy with the quark-gluon plasma, where the diffusivity is given by another formula that you might think has nothing to do with what we have. The diffusivity is predicted to be h bar c squared over T, where T is the temperature of the system. But it's actually the same formula the moment you realize you should just replace the rest energy, mc squared in our very non-relativistic case, by the kinetic energy in their system, which is ultra-relativistic. So you just replace mc squared by the temperature, and you see that the formula is just the same formula that we have. So we had fun measuring this diffusivity in this Fermi gas, and at low temperatures we indeed acquired a limit of spin diffusion with a diffusivity on the order of a few times h bar over m. And we also understand the high temperature behavior as what you expect from a Boltzmann gas that has, however, a scattering cross-section that's unitarity limited, with a scattering cross-section just given by the de Broglie wavelength squared, and not some number like the scattering length squared. The scattering length is out of the picture because it's so large at the Feshbach resonance. It has become infinite and drops out of the problem. It is nice to compare this to the diffusivity measured actually kind of recently in the quark-gluon plasma. This is data from last year from my MIT colleague who have measured the diffusivity in the QCD problem, in the quark-gluon plasma problem. And you shouldn't, worry too much about all the details on the plot, except that the diffusivity here multiplied by temperature, that would be the same thing if we multiply our diffusivity by m over h bar is on the order of a few. So some number on the order of unity. So that's really similar to a diffusivity measured in our lab. That's kind of a nice connection between two ends of the temperature scale, the ultra-cold Fermi gases and the quark-gluon plasma, also at very different density scales of many orders of magnitude density different. So now, this was a bit a brutal experiment. Can we actually find a way to make the system superfluid? But first, maybe there are questions.
Yeah, there are a few questions, Martin. Yeah, so
yes.
One is from Shubhankar asking, does the fermions from bound states just after the Feshbach resonance from negative to positive scattering length? So this is very first part of your talk.
Beautiful. Yes, so I will explain that. That's exactly what happens. These fermions can form bound states at the Feshbach resonance, or a little bit below. So already two fermions can form a molecule if you have a positive scattering length. There is a molecular state available. And we will see in the many-body case, they can form Cooper pairs. And they even survive in the region where two-body physics would not predict a bound state. So that will precisely be the topic of the next section.
Okay, so the next question is from Sabir Sachi. Can any different kind of trap will also work instead of harmonic trap for this experiment? I think it's asking regarding the mixing of the fermions.
Beautiful, yeah. So in the old days, we just happened to have a roughly harmonic trap because that was the convenient trap geometry we had at the time. It was formed by a magnetic trap in this axial direction. But as you saw in some other slide, these days we love to work with these box potentials where we use walls of green light to create a uniform potential. And that also works. Anything you can cook up with magnetic fields or optical potentials can work as a trap. So you can design your own trap and try experiments in any kind of trap.
So there's another question from Pratik asking why there's this factor of 5.8 h bar over t for diffusivity as opposed to just h bar over t.
Beautiful question, right? So in our case, it's h bar over m because we're non-relativistic. But why is it not 1 times h bar over m, but 6? And the answer is that this is happening in a harmonic trap, it turns out. It's a little bit a slightly complicated story, but we don't have uniform densities smashing into each other and penetrating each other. But there's a high density region in the center of the trap and a lower density region in the outskirts. And therefore, you can imagine in the lower density regions, you effectively have a weaker interaction than in the center. And you can have faster mixing outside than in the center of the trap. And if you average over this non-uniform distribution, you actually get a factor of roughly 2 pi, turns out, in the calculation of the diffusivity. It's a bit of a slightly complicated story, but you can read on it in the supplemental material of our paper from the time. You will find it on the archive, much easier than in the actual Nature publication, where we actually find that factor and explain why it's not on the order of 1 times h bar over m, but 6. If you did the experiment in a box potential, you should find on the order of 1. And I will a bit later talk about experiments on sound diffusion in a box potential, where we indeed find this factor of on the order of 1 instead of 6. It's a beautiful question.
So Maitreyi is asking, do you get other kinds of currents that are interesting for fermions of higher spins?
So yes, what kind of currents could we imagine? First of all, for the spin 1/2 system, I showed you spin currents, interesting, but of course we can also ask about density currents, so sound, right? And I will talk about that. Heat, I hope to be able to talk about that. That will give us transport coefficients like the viscosity and the thermal conductivity. If you have even higher spins, which you can imagine doing, so in principle, you can imagine having experiments on 3 or more spin states. You can also imagine having a higher order or more complicated spin currents in these higher spin systems. Absolutely. I will tell you it's
yeah, please go ahead.
It's a beautiful question. It's suddenly much harder to study strongly interacting 3 or higher spin systems than 2 spin systems. And that's because of one detail I didn't tell you about Feshbach resonances. Usually, if you do this with bosons and you go to a Feshbach resonance, your system explodes. You have 3-body collisions from hell. You have strong 2-body interactions, but even higher, even stronger 3- and 4-body collisions, and so on. And the whole system collapses. Why does that not happen with 2 spin states of fermions? Because of the Pauli principle. If you have only 2 spin states that can scatter, a 3-body collision will require at least 2 spins having the same spin direction. So it has to be 2 spin ups and a spin down, for example, colliding. And that cannot happen at short distance. The 2 spin ups cannot be in an S wave. So this is suppressed at low temperatures thanks to the P wave barrier. But the moment you have 3 distinguishable spin states available, now you can again have collisions from hell. And this has been measured by Selim Jochen in a beautiful experiment a while ago, that 3 fermions in 3 different spin states actually again have very strong 3-body collisions. And so we have not been very good at the moment to study higher spin systems with strong interactions for this reason.
So there's another question, last one maybe. So Kumar Gupta is asking that, I think regarding those non-interacting part, that fermions are expected to have infinite repulsive potential when they're almost touching each other. So what explains how they pass through each other as shown in the movie clip?
It's a beautiful question. Yes, they have basically infinite repulsive potential when they're almost touching each other. It's just extremely unlikely that they touch each other. And at low temperatures, you have to always think about probabilities of scattering with each other, and not, and not take it too literally that these are billiard balls scattering, but instead they're described by waves. And the waves are described by the de Broglie wavelength, telling you what's the characteristic uncertainty with which each particle is somewhere. So if you then ask, great, what is the probability that they ever meet at that short range where they would have such a strong scattering? It is minute, it's completely negligible. And all that you have to do is to ask, what is the overall phase shift that the 2 waves acquire as they meet and leave each other again? That's the only thing that happens at low temperature scattering. And it turns out that scattering phase shift, that depends well on the exact shape of the interatomic potential, but can be described by just one number, the scattering length. And as you could see, that scattering length can even be tuned to be 0. So you can make sure that there's 0 net effect of the 2 clouds moving through each other. So it's a little bit, you have to put yourself into this wave scattering mindset in order to see that this infinite repulsion at very short range has just a negligible influence on the scattering.
I think you can go ahead, and we'll have the set of questions again once towards the end. Beautiful
questions. It's really wonderful. Yeah, so I would like to ask whether now we can also see how these Fermi gases can potentially become superfluid. Well, the answer is yes, of course, because electrons are fermions, and we know since 1911 that electronic systems can become superfluid. That was the discovery of superconductivity by Kamerlingh Onnes in 1911. So he saw, and rather I should say some poor student in his lab saw that the resistance of metals at low temperatures dropped suddenly to unmeasurably small values. He fired that student repeated that experiment and found that the student was right and got the Nobel Prize for it. I hope I'm not completely mischaracterizing this history, but I once heard about this story and it's too good not to retell. It took a tremendous amount of time to understand what was going on. It took almost 50 years before Bardeen, Cooper, and Schrieffer could put the pieces together and understand why these fermions, these electrons, can form a condensate of pairs. This is the famous theory of BCS superfluidity. And they figured out, yes, that superconductors are just charged superfluids of electron pairs. And the frictionless flow that you know maybe from superfluid helium-4 is just the equivalent of having this resistanceless current of these charged particles. The same theory with beautiful additional ingredients due to the non-S-wave scattering in helium-3 explains superfluidity of helium-3, discovered by Lee Osheroff and Richardson. And they got the Nobel Prize for that discovery as well. We also are pretty strong believers that neutron stars are superfluid. They are at low enough temperatures to be superfluid, and people speculate that in the core of neutron stars you might even have a quark superfluid. So how does that come about? Just told here in a little cartoon. For bosons, we're kind of happy. We have an idea of how you can get superfluid. Bosons can form this wonderful Bose-Einstein condensate at low temperatures, where they all basically occupy the ground state of your system, in this example, a harmonic trap. And this happens the moment you become degenerate. So the critical temperature for formation of condensation, and therefore formation of superfluidity, is just the degeneracy temperature scale, which I called the Fermi temperature before. It's a bit confusing, but that is the degeneracy temperature scale that you need to reach to make bosons superfluid. But hey, among friends, bosons are just fermion pairs, right? They're strongly interacting, tightly bound pairs of, well, in the case of hydrogen, an electron and a proton, or a sodium ion and an electron. Or, and that happens in our lab, a lithium-6 atom and another lithium-6 atom, forming a lithium-6 molecule. So for those, we should expect a critical temperature on the order of this degeneracy temperature scale. In the BCS kind of mindset, we have very weak coupling between fermions. Clearly, I should, in the easiest example, take two kinds of fermions, spin up and spin down, and let them weakly interact. So each of these species forms at first a Fermi sea, but then it turns out once you switch on weak interactions, Bardeen, Cooper, and Schrieffer has shown that the system is, this Fermi sea is unstable towards forming lots of beautiful Cooper pairs. And that pairing is, unfortunately, for weak interactions, very fragile. It's exponentially fragile. And so the critical temperature of superfluidity in this BCS case is, it still scales with the Fermi temperature, yes, but it's suppressed with this terrible exponential factor, which goes like e to the minus something divided by KFA. We know what those are. KF, that was the inverse interparticle spacing. A was the scattering length. So if you have a scattering length that's much smaller than the interparticle spacing, it will be almost hopeless to observe superfluidity of fermions. But if your scattering length can be made to be large or comparable to the interparticle spacing, now you have a chance, because now the temperature for superfluidity is on the order of the degeneracy temperature scale that people taught us how to reach already in 1995, when the first Bose-Einstein condensates were created in the labs of Eric Cornell, Kyle Wyman, and Wolfgang Ketterle. And that's precisely the hope that we can have given these Feshbach resonances. We can tune this interaction parameter, 1 over KFA, the interparticle distance divided by the scattering length. And if we are over here, if this number becomes very, very small, much smaller than -1, that minus means attractive, and much smaller than -1 means very, very weak interactions, we should have this Bardeen-Cooper-Schrieffer state of very fluffy Cooper pairs, very weak binding, very fragile Cooper pairs, which are bound over very large length scales. As we make the interactions strong, we reach this regime of pairs that are on the order of the interparticle spacing. That's a strongly correlated soup where probably particles change their partners all over the time, but it's still a happy superfluid. And over here, for very strong binding between the pairs, we have the situation of molecules, which of course are bosons. So we are not surprised that these will form a Bose-Einstein condensate at low temperatures. So just by tuning the magnetic field in the lab, you can cross over from one to the other regime, from weakly interacting fermions to strongly interacting fermions, strongly interacting bosons, and to weakly interacting bosons. What about the critical temperature you have to reach to get a superfluid? Well, over here, if the interaction parameter is such that you have a bound state, so the scattering length is positive, the critical temperature is just that of Bose-Einstein condensation. So that's in principle then easy to reach if you just use the techniques that have been developed for reaching degenerate gases. And over here in this BCS regime, the critical temperature drops exponentially with the scattering length, so it becomes harder and harder in this regime. We can explore with our experiment this crossover regime all the way up to an interaction parameter on the order of -1 before the temperatures become too brutally low to achieve superfluidity. It's very nice to compare the critical temperatures for various Fermi systems compared to the Fermi temperature. Conventional superconductors, they become superconducting at a few Kelvin. That's 10 to the -5 or 10 to the -4 times the Fermi temperature of these systems. Superfluid helium-3 is more strongly interacting. It has a ratio of the critical temperature to Fermi temperature of 10 to the -3. High TC superconductors are on the order of 10 to the -2, whereas our high TC superfluid, it is on the order of 0.2. A more precise number is 0.17 that we measured a few years ago. I should also say this slide is a bit outdated. There's a new Fermi system, electron system, available, created in my friend's lab at MIT, Pablo Herrero, who managed to make a superconductor out of twisted bilayer graphene. And these days, even twisted trilayer graphene. And they reach a temperature which is 0.12 times the Fermi temperature, which is the limit what you can expect to get in a two-dimensional material. It's a beautiful story. And of course, I should add that to the slide. How can you prove that you have a superfluid if you think you might have one? Well, you should rotate it. If you rotate a normal fluid, well, you rotate a bucket of water, you will just get, maybe a nice meniscus of the water surface, which is cute, but you won't see anything too spectacular happening. If you rotate a quantum fluid, it turns out you will see these wonderful singularities, vortices piercing through the bucket. This slide is, by the way, borrowed from Wolfgang Ketterle, who has had fun rotating Bose-Einstein condensates in the 2000s. Superfluids, why do they develop these vortices? Well, number one, they don't want to rotate in the first place. They don't want to suddenly have some dislocation pop up in the center. They are single wave functions. The only possibility for having rotation enter a superfluid is through singularities in these wave functions, vortices. You can call them mini tornadoes, quantum whirlpools, how you want. And the reason is the wave that these superfluids are described by, that has to always close in itself, as any wave has to, just like a vibrating rubber band, for example. Only integer numbers of wavelengths are allowed as you walk around in a closed loop in your superfluid. So as we would say, the snake has to bite in its own tail, and the outcome the outcome will always be some number times 2 pi, which is the reason why there are 2 pi's in this image. It's a hilarious joke. I hope you appreciate it. Which is the outcome when you ask about the phase that you pick up as you walk once around a closed loop in your superfluid. So now the circulation is only possible in certain units in quanta carried by the vortices. So you might think that the superfluid solves this constraint by, in this fashion, having just a situation where you run around outside here, you get 5 quanta, maybe you run around a little bit closer to the origin, you wrap around 3 times, something like that. That's not how it happens. Instead, it happens in this fashion. It is energetically preferable to distribute the vorticity throughout your system, have many singly quantized vortices where each walk around one vortex gives you 2 pi of a phase acquired. So each of these vortices carry 1 unit of circulation. Why are they not all on top of each other? Why don't you have one big whirlpool in the middle? Well, then you would have n times the velocity surrounding this whirlpool, and therefore n squared times the kinetic energy for that whirlpool, compared to just n times the energy if you distribute them evenly over your system. So that's why they have to stay apart, these vortices, and orient themselves in this beautiful crystal lattice. This crystal lattice has been seen in bosonic gases and fluids. On the left side, the beautiful experiments by Packard on helium-4, visualizing these vortex lattices for the first time in superfluids. On the right side, the beautiful experiments by Jean Dalibard and his team in 2000, displaying quantized lattices of quantized vortices. And also, of course, because superfluids under rotation are completely equivalent to superconductors in a magnetic field, because of the analogy between the Coriolis force and the Lorentz force. They look the same, V cross omega, V cross B. The physics must be the same. So indeed, the first image of a vortex lattice came from superconductors in 1967 with this beautiful image of magnetic flux lines penetrating through a superconductor, also forming this nice apricot of lattice. So this was now the experiment Saikat mentioned from the PhD I was fortunate enough to do with Wolfgang, where my goal was to show that we had a superfluid. So we rotated this gas in our trap using 2 spoons. The spoons were, of course, also laser beams. And the hope was when we expand the gas and we would take a picture, we should see a vortex lattice. So let's do the experiment. We start here with a cloud of atoms. We take some PowerPoint spoons, let them run around a few times. And after you wait for about a second, you see a beautiful vortex lattice appearing in the soup. And that demonstrates superfluidity in gases of fermions. This works in an entire regime of parameters, both in the regime where you have tightly bound molecules and also in the regime where you have weakly bound fermion pairs, where 2-body physics does not support a bound state anymore. Great. So this is fun and nice to have a direct visualization of superfluidity. I would like to now focus on the unitary point, where we have the strongest interactions ever. Precisely this situation here of an interaction parameter 1/kFa 0, meaning that the scattering length has gone through the roof, is out of the picture, and I only have the interparticle spacing and the de Broglie wavelength giving me a length scale. So that's the unitary Fermi gas. It's a beautiful substance, strongly correlated fermions, but in some ways simple to describe. I only have these 2 length scales, the interparticle spacing and the de Broglie wavelength. Correspondingly, we have 2 energy scales, the Fermi energy and the temperature. If you ask about the equation of state, it must also be kind of simple. First of all, the critical temperature must be some universal number times the Fermi temperature, because there's no other energy scale available, and we measured that number to be 0.17. Also, at 0 temperature, we know the energy of the system must be some universal number xi times the energy of a non-interacting Fermi gas. Again, because at 0 temperature, I only have the Fermi energy as an energy scale. And we measured that number to be 37%. It's smaller than 1 because of the attractive interactions. But it's hilarious to note that 20 years ago, it was not known whether the gas, such a gas with resonant interactions, was even stable. So it's kind of wonderful that cold gases could immediately, like a few years after the question was posed in nuclear physics, provide an answer that these gases with strong interactions, a spin 1/2 gas with unitary delimited interactions, is actually stable. And I mentioned before the various superconductors. And so here is actually a slide from my friend Pablo's paper on the observation of superconductivity in twisted bilayer graphene, where lots of substances are shown here that have a high critical temperature compared to the Fermi temperature. The twisted bilayer graphene is very close to the BEC critical temperature, and our gas here, lithium-6, is the one closest to that line, showing you how this gas is a very strongly correlated Fermi system. So we saw already the story of the quantum limited diffusivity in the first part of the talk. This diffusivity should extend to other coefficients, other transport coefficients. It should not only be there for spin, it should also govern charge, momentum, thermal diffusivities. So let's do more experiments on transport and to see what we can learn about these transport properties. And so this is now an experiment on sound in such strongly interacting Fermi gases. And I'm happy to mention here the heroes of that experiment: Parth Patel, whose family, by the way, is in India right now, Zenji Yan, Biswarup Mukherjee, and Richard Fletcher and Julian Struck. The experiment we have done here is very similar to the one you see in the movie in the upper left corner, which is you want to just create waves in your box of fermions. So in this experiment, we literally have a box and we want to shake it up. So how to shake that up? Well, easy enough. You push the atoms on one side of your trap and create sound thereby. And it's literally what happens. If you look at the image, after shaking, it looks like there's a little bit of sound. Yes, if I take the ratio of the two images, the shaken and the unshaken one, you see these very nice ripples of sound waves. This is now no longer spin, by the way. Red and blue now encode simply high and low density regions, right? And if you draw the density difference as a function of distance, you see the undergraduate textbook sound wave propagating through your system. Oops. Sorry. You see that this sound wave is damped. Sound diminishes from the left to the right. And that's precisely what I'm after, because I know sound is damped by viscosity. So learning about the damping of sound will teach me about the viscosity of the gas. First things first, let me prove to you that this is true and honest sound. I vary the frequency with which we shake, and this changes the wavelength that the gas responds at. So this can be done directly. You take images after shaking a little bit and you get different wavelengths created in the gas, as you can directly see, and you can measure the dispersion relation, the frequency at which you shake versus the inverse wavelength that you observe, and it's nicely linear and giving you a very nice precise measurement of the speed of sound in the system. There's a hilarious detail that I want to mention, that somehow Einstein was not quite right when he wrote down that E equals mc squared. It turns out E equals 9/10 of mc squared, if you didn't know that. It's of course very confusing. We are now correcting t-shirts that are printed all over the world where people write E equals mc squared. We write the little 9/10 there. You can buy that t-shirt from us if you want. And what is going on? The story is, of course, that c here is the speed of sound, not the speed of light. And m, the mass of the particles times the speed of sound squared, should be, as usual, calculated by taking the derivative of the pressure of your gas with respect to density at constant entropy. Now, that is a complicated question for the strongly directing Fermi gas, but I know that my gas is universal, it's scale invariant. So the pressure has to be some universal number that may depend on the entropy times the pressure of a non-directing Fermi gas. But I keep the entropy fixed, so I can take that out of the derivative, and all I need to know is how a non-directing pressure depends on density. And I know that from the textbooks. It gives me just a 5/3 in front. So mc squared is 5/3 times the pressure divided by density, or 10/9 times the energy per particle. And that's why we obtain a nice relation between the energy per particle and mc squared, which is m times the speed of sound squared. And indeed, if you plot our measurement on axes where the energy per particle goes from 0 to 9 and mc squared goes from 0 to 10, you get a nice line, a nice diagonal, and the measurements all lie on this line. Next thing we want to do, we want to see whether we can excite resonant sound modes in this box. So we shake the system periodically and we see whether there are resonances in the box. And yes, every time we hit a resonance, we get beautiful standing waves appearing in that box. So by the way, we shake the system with frequencies on the order of hundreds of hertz, which I could sing to, by the way. And I always make this hilarious joke, which I find hilarious, that we should use Bose loudspeakers to talk to our gas, for example, to vibrate the mirrors that we use to form our optical trap, and it would shake the system. And when we hit the resonance frequency, we should find a standing wave of sound. And of course, we should use Bose loudspeakers and not some other company's speakers. Great. So once we find these resonances, we can actually take these images, integrate over the boring direction where nothing happens, and obtain these slices, which tell us whether or not a standing wave has been formed, and therefore form a sonogram of the unitary Fermi gas. So what you see here is just splicing together all these experiments at all the various frequencies together in one image, where you can nicely see the various resonances. You see the ground resonance, which is just the sloshing mode of atoms sloshing back and forth in the gas. This here is the first excited mode, the first symmetric excited mode, still kind of discrete. And you see at higher and higher frequencies, the modes become less discrete and less well defined. And that's also precisely because of damping. You can take the Fourier transform, the spatial Fourier transform here, to again figure out what are the special wavelengths that sit inside the gas after shaking. And again, you see this linear dispersion feature, the linear relation between K and frequency. But this time you also see that these resonances are broadened at higher and higher frequencies, telling you exactly about the stronger and stronger damping of sound at higher and higher frequencies. If you have very good eyes, you even see second harmonic generation here in this branch over here at 2 times the resonant frequency. So at this point, I want to maybe ask what can we learn about the system from these measurements? And so we need to understand what are the hydrodynamic equations that govern the system. There's certainly the continuity equation at work. We are not losing any particles, good. So that means mass is conserved. And whenever I see the density locally change in time, that must be because some current has transported particles away from that local region. So I get this characteristic continuity equation. I also have momentum conservation, which means that whenever I see some particles getting some current changing locally in time, that must be because there is some pressure differential acting on my piece of fluid, or there is actually damping. So what I'm writing down here is the Navier-Stokes equation, telling me how viscosity can damp the fluid motion. This is actually a simple version of the equation. Often you also have to include bulk viscosity. But in our gas, bulk viscosity is absent. Bulk viscosity is something that would increase your entropy as you dilate your gas in every direction equally with the same dilation coefficient. But in our scale invariant gas, this will not change the entropy of the system. So it will not cause dissipation. Therefore, there is no bulk viscosity. So it's actually simple. There's only shear viscosity, which is the same viscosity you would measure when you drag a sheet through your fluid, and you ask how far away from that sheet would you still notice the sheet having been dragged through. So how far away from the sheet is the velocity still modified because you dragged the sheet through? So that's the shear viscosity. And there's a third equation which derives from energy conservation, which is the transport of heat. So entropy is dragged around, and it also comes with a dissipation coefficient, the thermal conductivity, which can also increase entropy. And those three equations together give you a sound mode, which is damped in a characteristic way due to both viscosity and thermal conductivity. So the sound diffusivity carries both information of viscosity and thermal conductivity. And the dispersion relation that comes out of these three equations is, well, almost linear. Omega is almost C times K, but not quite. There is this damping process, which gives you an imaginary coefficient on this frequency, telling you that the waves will be damped with the characteristic damping rate, which is this diffusivity times K squared, the wave vector squared of the sound wave that you're running through. So at higher and higher frequencies, as you send around higher and higher wave vectors of sound, your damping rate should go up quadratically with the wave vector. And the ratio of damping rate and K squared, that gives you the diffusivity. So I can now show you these measurements, a direct measurement of these sound resonances that you have just seen, just here plotted for each different mode. And you can directly see, yes, at higher frequencies, I have more and more damping. I have broader and broader resonances. And I can plot this damping rate versus the frequency. It's quadratic, and therefore I can obtain the diffusivity. Now you see the units that we have here are very human scale, like hundreds of times per second is the typical damping rate. And the frequencies are already set I could sing to. It's hundreds of hertz, or omega would be 2 pi times that, so on the order of 1,000 per second. But if you take the ratio of gamma divided by the characteristic K squared, you get a diffusivity that you best describe in units of h bar over m. That's kind of cute. I have very human scale measurements, but then I obtain a diffusivity that's expressed in terms of Planck's constant divided by the particle mass. Here in this example, at this temperature, you find 2 times h bar over m. And this is, of course, related to this quantum limited diffusivity we have talked about before for the spin diffusivity. It's also related to viscosity being quantum limited as measured by John Thomas. And there's a whole range of theory explaining this quantum limited diffusivity for these Fermi gases. Right, at this point, I can also compare to viscosity of other superfluid substances, for example, helium-4. Helium-4 has a kinematic viscosity that is given in these units of meters squared per second times 10 to minus 8. Well, I wish they had used units of h bar over m, because then this graph would have units on the order of 1, 2, 3 instead of 10 to minus 8. Indeed, superfluid helium-4 has quantum limited diffusivity of its momentum. By the way, you don't see in this graph where superfluidity kicks in, which is roughly around this kink here, around 2.3 or so Kelvin. It doesn't leave a very stunning mark in the viscosity. And if you are worried, wait, I learned that superfluids have zero viscosity. That's only true in narrow capillaries, where the normal fluid is pinned to the walls and the superfluid can flow without friction. In a bulk container of superfluid, you will of course still have viscosity thanks to the normal fluid carrying around the excitations. What about helium-3? I mean, after all, we have fermions. I should compare to helium-3, not to helium-4. A totally different story. At very low temperatures, once the gas of helium-3 becomes liquid, you see that the viscosity rises dramatically instead of dropping. It rises because helium-3 becomes the world's best Fermi liquid. Pauli blocking sets in, so collisions become less and less frequent, and the gas or liquid is less and less able at dissipating momentum. So you drag a sheet through helium-3, even far away from that sheet, you will still notice that you were dragging through this sheet. And characteristically, the viscosity grows like 1 over t squared, precisely like the collision time that is extended in a Fermi liquid, because only the few particles near the Fermi surface can still collide. Where's h bar over m on this scale? It's down here. H bar over m is still the correct rate around where it becomes liquid, but in the end, helium-3 has a viscosity that's much, much larger than that. Now, what happens at the superfluid transition? There is a tremendous drop in viscosity by a factor of on the order of 10 or so, starting from the superfluid transition point, which is this point here. It drops significantly, yes, but then you can still ask, what is the remnant viscosity of helium-3? It's still thousands of h bar over m. So helium-3, even in the superfluid regime, is still sticky, if you want to say it that way. This is our result. Our measured sound diffusivity of our unitary Fermi gas, the Fermi gas right at the Feshbach resonance, it only drops with temperature. It doesn't rise with temperature. It never shows this Fermi liquid-like behavior. It only drops, and at some point acquires a constant diffusivity on the order of 1 times h bar over m. That is the situation for sound diffusivity, and that is, again, a story of quantum limited diffusion. It's much more in line with helium-4, a boson, than with helium-3, the fermion, because of the very strong interactions, which mean that the Fermi surface never becomes very sharp. Collisions are never strongly suppressed, and before they could get strongly suppressed, the gas becomes superfluid and forms a pretty stable Fermi distribution, which looks roughly like a Fermi gas that has a temperature on the order of the pairing gap. The pairing gap being very large, comparable to the Fermi energy, gives you therefore a diffusivity that is on the order of h bar over m. So I think that might be a good place to stop and ask for questions, because the next story will be about how do you see superfluidity in such experiments. Just wanted to quickly mention that theory is able to describe the high temperature region of our measurements quite well by now. These are theories that have come out after our experiment. At low temperatures, there are still some discrepancies, but the theory becomes very difficult at low temperatures also. But so this is an interesting story to follow, how much theoretical calculations can explain these measurements. So I stop here and take questions.
Yeah, so I can see one question. I think your clarity was so amazing. People are still stunned. So one question from Arnav: what is the meaning of singularity at the center of vortices? What happens there?
Oh, beautiful. Yeah. Mm-hmm. So if you take a wave function and you now say, I want to rotate it. I want to put angular momentum in it. Well, that means you have to wrap around the phase by 2 pi inside that wave function. But if you think about it, that cannot happen just like that. You cannot distort a homogeneous wave function without singularities and suddenly have a 2 pi phase twist somewhere. It will mean somewhere there is a singular point where the velocity would go through the roof. So actually, singularities can only come from the outside, entering the wave function. That's precisely what happens to our vortices. They come from the outside, enter the wave function, and now, yes, you can have a happy 2 pi phase twist, but right there in the center, you have to have 0 as the value of the wave function. Otherwise, the wave function would not be well defined right at the center of the vortex. So it's a 0 in the wave function, where everywhere outside, if you take a path surrounding that 0, you will pick up 2 pi or an integer multiple of it if you have a multiply charged vortex going around. So that's what I meant by singularities. It's really places where the wave function is exactly 0.
So there's another question from Kumar Gupta. What is meant by scale invariance in the systems, and can there still be bound states in spite of scale invariance?
Yes. So scale invariance, it's a powerful thing. It means that you no longer have an interaction-dependent length scale in the problem. There is no longer a van der Waals range that's relevant or a scattering length that's relevant. All these things are out of the problem. The scattering length has gone through the roof, and you only have the interparticle spacing and the de Broglie wavelength, which is related to the temperature, as your length scales. So that's very powerful, because then you know any energy scales that you can cook up must be given by, for example, the Fermi energy times any dimensionless function of the ratio of Fermi energy to temperature, for example. So that's what's meant by scale invariance. You can cook up, given a particular system of fermions with certain distances between them, you can cook up an equivalent system at exactly the same entropy if you scale all the dimensions of your space, x, y, z, by the same factor. And you will get another system that has the same entropy and is equally well a solution to Schrödinger's equation. That would not be the case if you had a finite scattering length, because that scattering length would tell you whether you have made the system more dilute or less dilute. But without that length scale available, you can do this scaling and it will yield another solution of Schrödinger's equation. It's extremely powerful. Can you still have a bound state in spite of scale invariance? Yes, why not? That bound state energy, whatever it is, must be some universal number times the Fermi energy, at least at 0 temperature. That's still allowed, that would be a happy bound state. And indeed, there is this bound state. There is still a solution for the Cooper pair binding energy, or in other words, the pairing gap at this resonant place. So the pairing gap is actually on the order of 40% of the Fermi energy. So it's a very robust superfluid of fermion pairs.
Yeah, so there is another question from Professor Bimalendu, that you made comparison of nuclear matter and Fermi gas, but superfluidity in nuclear matter also has this finite range effects. So any comments on how to explore finite range effects in Fermi gas superfluidity?
A beautiful question. So that is the fine print indeed when we make these statements. Already in this dilute neutron matter, we know, yes, the scattering length is much larger and negative compared to the interparticle spacing. That's good. That puts us close to neutron matter, but there is a finite range between neutrons, which is also on the order of the interneutron distance. The same is true for other nuclear matter. So that certainly has an effect. Actually, in terms of the energy of dilute neutron matter, it doesn't seem to be a strong effect. So people have done calculations putting in finite range effects, and they found that the energy of dilute neutron matter is within 10% what we have in our universal gas without the finite range effects. So there are certainly there are corrections, but they don't seem to be so strong. And in terms of the energy, it's a 10% effect. Can cold gases possibly simulate finite range situations? In the future, I would hope yes, because there are Feshbach resonances where you do not have a negligible finite range, but where you have sizable finite range effects. And these are things that are explored these days. For example, Joseph Stuyvesant is studying P-wave Feshbach resonances, which have a sizable finite range. And in principle, one can hope to study Fermi systems with finite range effects. How much tunable these finite ranges will be, also independent of the scattering, that's not absolutely clear. It seems like these two things might be tuned together. But certainly there are systems where we expect finite range effects.
Okay. I think I'm sure there are other questions that would pop up. People are just warming up, but we are also out of time. It's exactly 9:30 Indian time. So we may wrap up now unless Martin wants to make any further closing comments for Monday's lecture. So we'll all meet there.
I'm very happy seeing you on Monday, where we continue this story.
Absolutely, yeah. It was a pleasure for all of us. On behalf of everyone, I thank you, and see you on Monday then.
See you on Monday.
This discussion. Okay, great. Thanks.
All the best. Bye-bye.
Yeah, so I guess we can.
Yes, we can go now.
Yeah, I personally have no time constraint. If
okay, Martin, then I had a very simple-minded question. Like when you showed the dispersion relation, this is your latest work, the sound. So there it seems like, the imaginary real parts, you had a diffusion and the velocity of sound. And from like simple-minded Kramer-Ströning, I would then think that the diffusion and the velocity of sound would be related. So if one scales, the other would also. Or maybe I'm just thinking it wrongly.
And so in this, maybe the theory.
I think after your Navier-Stokes, this couple set of equations.
Yes.
Yeah, exactly. This one, omega square. Or maybe, yeah. Maybe there's an omega sitting there, so maybe it's somehow it just seemed like then as your diffusion is constant is changing, you would see that signature in the velocity also.
Mm-hmm. Yeah, I guess it's a question of what one holds fixed. Yes.
Yeah, I guess so. Maybe.
Yeah. So the speed of sound is just from the in this little model will just be given by the equation of state. So how the pressure depends on the density, and that's the C thing. And the diffusivity depends on the viscosity and thermal conductivity. But of course, how much, for example, of the thermal conductivity I get into the diffusivity is governed also by the equation of state. Here's a very particular formula, which is only true for the scale invariant gas. But if you look up the textbook, the thermal conductivity is multiplying things like the difference in the specific heat, constant pressure, and constant density. In other words, it brings in the expansivity of the gas. How much does the density change as you change temperature? That tells you how much the thermal conductivity plays into the diffusivity. So these things are certainly linked, but at least in the mindset where I write down these equations with external parameters, viscosity and thermal conductivity, I don't see how the diffusivity, I mean, the diffusivity has those parameters in it. I don't see how the speed of sound would get corrections due to viscosity and thermal conductivity. I think in the microscopic theory, yes, there can be this coupling. So the microscopic theory, whatever it may be, right, it will give you both the viscosity and thermal conductivity, and it will give you the speed of sound. And I'm sure they're sort of, when one changes rapidly, the other will change rapidly. But here we have this mindset that we don't actually know anything about the underlying theory other than we have the equation of state, and we have these parameters given to us from the outside, viscosity, thermal conductivity. Then we can write down what the diffusivity is, and we can write down the dispersion relation.
And also there might be relation if they're kind of analytic, but you kind of seem to also have a kink on D at some point. So maybe that also.
Right. So maybe
so there might be discontinuity. So Kramer-Ströming
yes,
might not be valid here. That way.
Yes. Yeah. So you might think about the superfluid transition, for example.
Yeah.
Yeah. So you will like the continuation of the story on Monday as I go into the superfluid, because there's a surprise there. In the first sound diffusivity within our resolution, which is not very great, we don't see any discontinuity. We also don't see a discontinuity in the speed of sound, but even in helium-4, they required a sensitivity on the promille level to be able to see a discontinuity in the derivative of the speed of sound. So the speed of sound indeed has a little kink, and but at
those kind of things will break down,
which we don't see. But on Monday I will talk about second sound and second diffusivity. And to our surprise, it's actually still unpublished, but I'll show it on Monday anyways. We haven't even sent the paper around. But it's super cool that we see the second sound diffusivity have a little kink at TC.
And from the vortices, like this older experiment, is there a possibility this too simple-minded maybe of getting any information of viscosity, diffusivity, like from the lattice structure and so on? Like, did actually you try or did?
Very cool. So we did measurements at the time of the spin down time of the vortex lattice. How quickly do the vortices eventually go away? Because eventually our trap is not perfect, so we're not conserving angular momentum perfectly. Also, there's a bit of heating going on, so the vortices eventually will give up some energy to the phonons in your soup and leave the system. And that was interesting to measure that near the unitary point, the vortices lived the longest, for sure. But I don't think anyone tried to model this with some theory of viscosity.
I think in some of these condensed matter systems, people have seen things diffusing, or these vortices diffusing around. But in cold atoms, I guess things are like finite size, much smaller. So maybe, I don't know, with better imaging technique and so on, do you see them moving, or just a single shot?
It's always a single shot, but you can ask, because in every shot we generate the same number of vortices quite nicely. How long does it take for them to disappear? So we know that time scale, and somehow I think you must be right that I should be able to learn something about the dissipative mechanisms. How quickly do the vortices give up their energy to the phonons in the system, which is interesting. I think it gives rise to, it is controlled by new things, namely the vortex-phonon coupling.
So, yeah.
And now we should actually look into this. It's a super cool question. Somehow I don't think people have tried to learn from our spin down time something about this. Maybe it's difficult, I don't know. But I like the question very much. It's we should learn something, yeah, from that.
So it was a great learning experience, Martin. It was just absolute clarity. In fact, few people, like one comment I saw earlier, that it's just going like a story. So it was really, really nice.
That's nice, yeah.
Well, I think there are, like, I don't know, you just said, you called for it, that like you do not have a time constraint. So there is a question from Maitreyi, that how would I visualize phonons with angular momentum?
Visualize phonons with angular momentum. Okay, I'm not sure I mentioned phonons with angular momentum, but if you want to picture phonons with angular momentum, I will picture them just like light waves with angular momentum, which we know we can form light that has angular momentum built in, orbital degrees of freedom. And basically that would be a wave that also does not look like a simple plane wave or a spherically outgoing wave without singularities, but it would have a node or several nodes, and therefore have angular momentum in it. Not sure I talked about this though. Light with angular momentum looks like vortices. Yes, precisely. Yeah.
Yeah.
So phonons with angular momentum therefore would also look like riddled with vortices. Yeah.
And that would open up a whole new field, like the this spatial, like the angular momentum states of light, like that.
Yeah, I did mention vortices coupled to phonons. Yes, in some ways you can have this funny picture that vortices are funny states of many phonons coming together to produce a localized dip in your soup, right? In some ways you can think of vortices being actually a superposition of many phonons coming together to define a very localized object. So in some ways vortices are a whole superposition of phonons, but you know, they're people who consider you know, if you want to consider vortices as their own object, then you can ask, how do they scatter with a plane wave of phonons? So that would be phonons without angular momentum. But how would these plane waves be scattered by the presence of vortices? And that's then called vortex-phonon coupling. It's something where, to learn about it, one would have to open some Russian textbooks usually. And that seems to be the mechanism with which vortices can give up energy to the phonon bath, and thereby slowly spiral out of your system and leave the system.
Human Landau hydrodynamics.
Mm-hmm.
Okay, so I think we can. Yeah. So. No. Yeah, I think the question was this. We can take as the last question. So this would be would not be quantized. Needn't be quantized. Those.
Yeah. You certainly need to start with vortices be quantized, otherwise you get the wrong, thing. I don't know. I'm not an expert on vortices.
But that's like a classical quantization, right? Like exactly, it's a still open question in this the orbital angular momentum of light also, whether one can measure h bar there. Like there's a big debate I think still on whether those are actually quantum.
Okay. Maybe this is somewhere how it's going. Yeah,
just LM, YLM modes, like so. They have still the 2π quantization, but not a purely like there's no demonstration yet of h bar quantization, I guess.
Beautiful, I see. And this might be also where this question is going about the phonons, whether they have to be quantized. Yeah, I don't know. I think it's a beautiful question, and actually it's very inspiring. I should think about what we can learn from the spin down time of the vortices about precisely this coupling.
Okay, so I think we'll be very eagerly waiting for your Monday talk, and thanks a lot for, like in these hard times, to agreeing to be here, and it's great meeting you after such a long time.
It is wonderful, and I love the questions. They were all wonderful.
Yeah, great questions. Yeah. Okay, so yeah, and so we'll log out then for now.
All the best. Yeah, bye-bye. See you Monday.
See you. Bye.
Thank you.
Thank you.
Okay, Saikat.